Welcome. Today, we're going to build your personal algebraic toolbox. We're starting with the absolute fundamentals to help you really master polynomials and quadratics, one step at a time. Okay, let's be real for a second. Do you ever feel like you're trying to read a secret language? You know, with all these weird words like coefficients and degrees. Well, guess what? Today, we're cracking the code. We're going to give you the keys to understand it all fluently. First things first, what even is a polynomial? Think of this as the basic Lego brick for pretty much everything we're going to cover. It's fundamental. So what's the official definition? Well, it's just an expression made up of variables and numbers, all connected by adding, subtracting, or multiplying. But, and this is the big one, there is one forbidden move. You can never divide by a variable. That's the only rule you really have to remember. This slide shows it perfectly. Look at the left side. You've got 3x squared plus 2x plus 5. That's a classic polynomial, all good. But on the right, the second you see that 3 divided by x, it's out. That division by a variable is a total deal breaker. All right, now that we know what they are, let's look at how we tell them apart. Think of this as the blueprint we use to classify any polynomial we run into. It all comes down to something called their degree, which is really just a fancy way of saying the highest power of the variable. As you can see, if the highest power is 0, we call it a constant. If it's 1, it's linear. If it's 2, it's a quadratic, and we're going to be seeing a lot of those. And if it's 3, it's a cubic. See, it's a pretty straightforward system. So let's break one down right here. Take a look at this guy. 7x cubed minus 2x squared plus 4x plus 9. Just scan for the highest power you see. It's that little 3, right? So the degree of this polynomial is 3. And that number right out front, the 7, that's what we call the leading coefficient. Simple as that. Okay, now for the really cool part. Let's get into the remainder and factor rules. Seriously, think of these as secret codes in algebra that let you work way, way faster. So imagine you're staring at some huge, messy polynomial. Is there some kind of shortcut to find its factors without just guessing and checking forever? Oh, you bet there is. The first one is called the remainder theorem, and this is just brilliant. It says that if you want to know the remainder when you divide a polynomial by something like x minus a, you don't actually have to do all that long division. You just plug a into the function, and whatever number pops out, that's your remainder. It's a total game changer. And that leads us right into an even more powerful tool, the factor theorem. Just think about it for a second. If you use that shortcut and the remainder you get is 0, what does that mean? It means it divided in perfectly. So if f of a equals 0, then you know for a fact that x minus a has to be a factor. It's like a secret test for finding factors. Let's see this thing in action. Say we have the polynomial x squared minus 5x plus 6. Let's test the number 2. We plug it in, do the math, and we get 0. Boom. The factor theorem just told us that x minus 2 is a factor. Now let's try 3. We plug it in and we get 0 again, so x minus 3 is also a factor. We just cracked the whole thing. So why are we so obsessed with finding these factors anyway? What's the end game? Well, the whole point is to find the zeros of the polynomial. That's the real target of our search. These zeros, sometimes people call them roots, they're just the values of x that make it the entire polynomial equal 0. If you think about it on a graph, this is literally where the line or curve crosses the horizontal x-axis. These are super important points in the real world. And here's where it all clicks. If we know the factors are x minus 2 and x minus 3, what value of x would make that whole expression 0? Well, if x is 2, the first part becomes 0. If x is 3, the second part becomes 0. So the zeros are 2 and 3. You see? Once you find the factors, they basically just hand you the zeros. All right, let's bring this all together. Now that we know why we're hunting for these zeros, let's talk about the how. Let's get into the master tools for solving quadratic equations. But before we even start solving, there's this fantastic little diagnostic tool called the discriminant. The formula is b squared minus 4ac. By calculating just this one little number, you can know what kind of answers to expect before you do any of the hard work. It's like a crystal ball for the problem. So here's what it tells you. If that discriminant number d is positive, you're looking for 2 different real answers. If it's exactly 0, you're going to get just one real answer. And if it's negative, no real roots. You can just stop right there. You know there isn't a real number solution to find. Pretty neat, right? So how do we actually go find those roots? We've got three main tools in our toolbox. Number one is factorization, which we've already been doing. Number two is the legendary quadratic formula. And number three is a method called completing the square. And out of all of them, the quadratic formula is the absolute superstar. This is the one formula that can solve any quadratic equation you throw at it. No exceptions. You just figure out your A, B, and C from the equation, plug them in, and it spits out the answer. It's the universal key. So let's do a quick recap. We've built a pretty awesome toolbox today. We started by figuring out what polynomials are and how to classify them. Then, we uncovered those amazing shortcuts, the remainder and factor theorems. We finally understood what zeros are all about, and we armed ourselves with three solid methods to solve any quadratic. We've covered a ton of ground, but I want to leave you with one final question to chew on. Now that you know how to find the roots of an equation, what do you think they actually look like on a graph? That's the next adventure, connecting these numbers to a picture.